Let's go ahead and talk about something known as dimensional analysis. It's analyzing mathematical equations and expressions to explore the relationships between fundamental units. It's oftentimes done to verify that units are consistent and to tell us what types of conversions we're going to need to do. So we're going to talk about dimensional analysis in this screencast, and then we're also going to talk a little bit about it in the next screencast on conversion factors. I've got an example here that's going to show you what I mean by dimensional analysis. We have this calculation here, which is known as the Reynolds number. The Reynolds number is useful for characterizing flow in pipes. So you guys will learn a lot about this when you take fluids. Reynolds number is equal to the density, which is rho, Greek letter rho, times the diameter of the pipe, times nu, which is the fluid velocity, and then we divide that product by the fluid viscosity, which is mu. So we're going to just do a little bit of analysis here, dimensional analysis. The Reynolds number is unitless. So when we work with the units here, we're just going to kind of verify that the Reynolds number is in fact unitless. It has no units. So let's go ahead and analyze this. By the way, the SI units for viscosity are Pascal times seconds. So remember, when we have this hyphen here, that means that we are multiplying Pascal times seconds. So let's go ahead and take a look at the right-hand side of this equation. So rho is density. Density is mass, and I'm going to just write this as big M. And what I like to do, I'm going to write Reynolds number, and I put in square brackets an equal sign has units of, or has dimensions of. So it has mass, right? Density is mass per volume. Volume is a length scale cube. So density is mass, big M, don't get that confused with meters. Mass divided by length cube. All right, and then we also have diameter, which is a length scale. So we're going to multiply by length, that's diameter. We've got fluid velocity. Velocity is in length per time. So I'm going to put length in the numerator, time in the denominator. All right. And then finally, we have viscosity in the denominator. Viscosity is Pascal times seconds. So Pascal, I'm going to write this over here. Pascal is a Newton per meter squared, right? And you probably know that Newton is force, which is mass times acceleration. That's equal to, so a Newton is mass times acceleration. Acceleration is the length divided by time squared. 9.81 meters per second squared is the acceleration on planet Earth. So I'm just going to write that as mass times the length scale divided by time squared. And then we divide by meter squared, which is length squared. So I'm going to put this entire thing, I'm going to flip it upside down and put it over here in the denominator. So we have ML, mass times length, and then we're dividing by L squared times time squared. All right. And back over here, I wrote velocity as length over S. That should actually be time. So that's a time scale. And I forgot to include this S here. So a Pascal times seconds, we're going to have another time scale there. So we have M is for mass, L for length, T for time. So when we do this, remember I told you Reynolds number is unitless. So we can go ahead and cross out things in the numerator and denominator. So we have mass in the top and bottom. We have 2 T's in the denominator. We have 2 T's in the numerator, so we can cancel those. We've got 1, 2, 3, 4 length scales in the numerator, and we have 4 in the bottom. So this, what I just did here, you see that everything cancels, and in fact this is unitless. This is how we can go ahead and analyze dimensions. Another thing that people typically do is they work with units, and I'll show you this in the next screencast, but we could do something like if we had SI units, Reynolds number has units of, and I would write kilograms per cubic meter for density, times meters for length scale, times we have our velocity, which is meters per second, and then we divide by viscosity, and viscosity is Pascal seconds. We can do a couple conversions here, and you'll learn more about this, or you'll review more in the next screencast. But we have Pascal. A Pascal is a Newton per meter squared, so I'll put this meter squared on the top, so I can cancel the pascals. A Newton is a kilogram meter per second squared. So I'll put that on the top. And see, I'm breaking it down to our fundamental units in SI. So we have kilograms, cancel. We have 2 S's on top and bottom. I've got 4 meters squared on the top and bottom. So that's how we can kind of verify and work with units. So you can kind of go through, predict what the units of the answer is going to be. You can do quite a bit by just looking at the units. Thanks for watching, and I will see you in the next screencast on conversion factors.